Hi, I'm Amir Hossein Mirzabozorg, and in this video I want to talk about one of our premium tutorials named Simulation of Debonding in Abaqus by Cohesive Zone Modeling with 2D and 3D models. This tutorial has been created according to this thesis. Based on this thesis, the Double Cantilever Beam or DCB test is simulated. The thesis studies the damage propagation and delamination in DCB and ENF tests. This tutorial simulates and verifies the DCB test with the numerical and experimental results presented in the paper. About the tutorial's description, its duration is 2 hours and 15 minutes, and the size of its zip file is 359 megabytes, and its tutor is Amir Hossein Mirzabozorg. Now I want to talk about problem description. This is the geometry of the DCB test. And here on this edge, we will apply the displacement control loading, and here we have the initial crack, and here we have the adhesive material, and here we have the pinned boundary condition, and the length of the initial crack is 50 mm. According to the geometry and physical specifications of the problem, it will be modeled in 2D space according to the 1-2 view. This is the 1-2 view. So the out-of-plane thickness will be 25 mm. Also, it will be modeled in 3D space. As the thickness of the adhesive layer is small in comparison to the aluminum beam's thickness, we will use the traction separation formulation to describe the mechanical behavior of the cohesive elements. In the premium tutorial, I have talked about traction versus separation formulation. This equation belongs to the cohesive surface formulation, and this equation belongs to the cohesive element formulation, and the left side of both of the equations are equal. And by assuming the uncoupled form of both of the stiffness and elasticity matrices, we can write this equation. And then we have this equation, and finally we obtain this equation. This equation relates the stiffness of the cohesive surface to the Young's modulus of the cohesive element and the initial thickness of the cohesive element. In the tutorial, I have completely talked about damage initiation and damage evolution settings. Here we have both of the numerical and experimental results presented in the thesis. And at the end of the premium tutorial, I have obtained the similar force displacement curves. And this local maximum is probable due to an epoxy imperfection, and it will not happen in the numerical simulations. Now I want to talk about modeling procedure in this tutorial according to the reference thesis to model the DCB test. In the premium tutorial, I have created 4 models. 2 of them have been created in the 2D space, and 2 of them have been created in the 3D space. About the 2D models, one of them has been created using cohesive element, and one of them has been created using the cohesive surface, and both of them have been solved using the Abaqus standard solver. And about the 3D models, one of them has been created using the cohesive element, and one of them has been created using cohesive surface, and both of them have been solved using the Abaqus explicit solver. And this is the mesh of the 2D model using cohesive surface. And this is the final 3D model. And this is the von Mises stress contour of one of the 3D models. And this is the delamination contour of one of the 3D models, including cohesive surface. At the end of the tutorial, I have compared all of the obtained force displacement curves. As you can see, here we have 4 force displacement curves, and as you can see, they are similar to the presented force displacement curves in the thesis. How to ask your video related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We try to answer all questions regarding the video details in the comments below. You can contact me using Telegram or WhatsApp, or you can send email to me. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. And we can conduct high-quality simulations for your thesis, exercises, and industrial projects. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.